So in this video, let's understand what is a piezoresistive effect. In a previous module, we understood piezoelectric effect, and in both of these lectures we have the name piezo common. Okay, so piezoresistive effect, let me write piezoresistive. So as the name suggests, when you have a piece of metal, or let's say a piece of conductor or piece of semiconductor, in these two types of materials, when you press them, they experience a mechanical stress which results into mechanical strain, and due to that the resistivity of the conductor or a semiconductor changes in response to the applied mechanical strain. So based on these principles, you have piezoresistive accelerometers, and you have piezoresistive pressure sensor. So in metal, this effect is observed in some of the metal, but this effect is not as profound as it is in semiconductors. So the commonly used semiconductors for the piezoresistive effects or piezoresistor effects are germanium and silicon, and based on that the manufacturing of such piezoresistors takes place. Now, as you can see in this picture, is a typical process to manufacture or fabricate a resistor using a semiconductor material. So usually you have a p-type substrate or n-type substrate in which you can form n-type well or p-type well. So if you have p substrate, you have n well as shown in this figure right here, or you have n substrate, then you can have p well. So this n well is a typical n-type semiconductor resistor which will exhibit a piezoresistive effect when there is a mechanical strain it will experience due to the applied, let's say, a pressure or applied mechanical load. So what you can see here is that in this n well you have this n plus contacts at the two ends. These are called n plus contacts to make a solid ohmic contacts to this n well resistor. So you just have this resistor like this, with a resistor you have two ends, and this is a p-type substrate where x-axis or x-plane is as shown, and this is your out of plane. You can see here z, this is your z, is the z plane is in this direction as shown by the arrow, and y is the out of plane. It means out of this screen and back into the screen. So this is how your piezoresistors are fabricated and using the semiconductors. Now let's have some mathematical expressions to understand this more. So this is the formula. In metals you have a resistor R that will be equated to resistivity rho multiplied by the ratio of length over area. So usually the resistance of a conductor, let's say you have a piece of conductor, and the resistance of that conductor can be changed by altering its geometry. For example, you can alter the length of this material or the cross section area, and then you have a change in resistance. But what if you are able to alter the rho as well, which is your resistivity? So in metal, piezoresistive effect is not profoundly observed. It is also there, but it is not profoundly observed. But in some special cases of metals, that change in resistor due to change in resistivity is more in some special metals. But usually the change in resistance of the metal due to change in the geometry is often more. What about this equation that we see? So this equation tells us a resistivity, which is a constant, is given by normalized value of resistivity right here, del rho over rho, divided by applied strength per unit strength. So del rho is the change in resistivity, rho is the original resistivity, and this symbol is the applied strength. So you can see that whenever there is a change in resistivity for applied strength, you have a value. So in metal, this relationship is observed for a certain value of applied strength. Let's say del rho over rho, this relation is observed to be linear, and this is your rho, that is a constant, this one. So this is constant, therefore, because the relationship between applied strength and this normalized value of the resistivity is constant. So that's all about the piezoresistors. So we have seen that how piezoresistors can be fabricated using silicon microelectronics fabrication process, and silicon and germanium are the materials used for making the piezoresistors. Once the piezoresistors are fabricated, they have applications to be used as an accelerometer, for example, or pressure sensor. So in that case, you have a thin diaphragm that vibrates due to applied load, and because of that vibration there is a change in the resistivity of that semiconductor resistor, and therefore its resistance R gets changed. Remember, R is rho L over A. So here your dimensions L and A are constant, but your resistivity is getting changed. So that's your piezoresistive effect. Okay, and so hope you like this video. If you did so, do share with others and like and subscribe to the channel, and wish you happy learning.